Hello everybody, welcome back to High School Tutoring. I'm your host Manny today, and we're going to be talking about cliff problems. So this is probably going to be one of the last videos that I do on projectiles, and this one is basically, if you remember Thrown Up, where sometimes we'd have to do a problem where if it's going up and it would go farther down than what the original point was. So I'm going to show some intro stuff because there's like one or two things that we've added to this list. Here, so we now have this our dy cliff. So our meters are, it's a number of meters, or it's the height of a cliff. So that's all it's really going to be. It's just now we have another dy value to deal with, and I'll show an example graph really quick. Obviously we have trigonometry, same thing here. We're going to be using this a lot. We still use it obviously just to find our x and y velocities. So, and yeah, that's going to be very useful, and these equations obviously to find other values that we're going to need for any of these problems. So if we look at our example graph here, you can see that we have obviously a little cliff. We have a parabola here that's shot upwards. You can see it's thrown upwards at whatever angle, and it goes back down. But you can see it goes back to this point here, which is the farthest point down. It's this is the ground level. This is a cliff, which is a number of meters high, as we've just discussed. And these 2 points here are equivalent to each other. So this point is our starting point, and if it was flat ground, this would be our ending point. That's just something we can keep in mind when we're solving for these problems. So I have a problem that I'm going to show now, and it is literally just a cliff problem. It's going to use an example. It's going to kind of look like this, but it's not going to be as steep. So Luke throws a baseball from a cliff that is 25 meters high at an angle of 30 degrees from the horizontal at a speed of 30 meters per second. How far from the original point did the ball travel? So if I just quickly pull up a pen here, so if we grab this and then do that, let's do a reddish color. Yeah, that'll work. So if we've got that, I'll just select this, and here we go. So we're looking for a cliff. So the cliff is 25 meters high. That's something we should know. This is going to be 25 meters at an angle of 30 degrees. So 30 degrees, that means our theta, which this is not drawn to scale, is going to be 30 degrees. Okay. And how far from the horizontal at a speed of 30 meters per second. So our total velocity going up, so all of this is 30 meters per second. So that is our equation, and we want to find our d of x. So our d of x is our goal to be found. So our d of x is what we're trying to find out of whatever we have here. So obviously beginning, we want to find our x and y velocities, because obviously here you can see we need v naught x to find d of x, which is what we're looking for. So if we have, our dy can be left out for a moment. So cosines x, as it is the adjacent value to the theta, and sine value is y, as it is the opposite. So if you look at our trigonometry, we obviously have sine, opposite of right hypotenuse, and cosine, adjacent of right hypotenuse. So we're taking a look at this here, and so that means that if we are looking at 30 meters per second and 30 degrees, that means we could do 30 times the cosine and the sine of 30, and that's whatever equals the x, and then that would be meters per second. So, and then we do the same thing, but instead of cosine, we do sine. That'd still be 30, and that is equal to meters per second of y. So now we can just go into our calculators, and there's multiple ways you can write it out. I like to write it out specifically how I have it written. So 30, and parentheses cosine of 30, and then close parentheses twice. And then, so we should get about 26 meters per second here for the x value. And then if we do the same thing but with sine instead, so 30 cosine or sine 30 and close parentheses, we have about 15 meters per second. So you can check this if you want to. It's a little bit off. The 15 is exact, but for the x value, it's about 25.98 or something. We'll keep it at 26 though, just for the sake of simple numbers. So now that we have our x and y velocities, we obviously have one component that we can use to find the d of x. So what we got to do is now find the time. So here's how I like to find the time. I like to find the time looking for these areas first. I like to find the time looking for this top bit, and then finding the time of the entire bottom bit. But before we find time, we obviously got to find d of y, because this is our only really applicable equation that we could use. So we find d of y. We obviously know d of y is equal to v naught y squared over 2 to the absolute value of g. This is just taking it's just taking this problem and isolate. Well, not this problem. Actually, I'm not taking any problem and isolating. I think. Oh no, we're taking this problem and isolating because we don't have time. And isolating this problem is because see here we have we have vy squared, which is going to be 0 in this case if we're looking for the top point. So that cancels out. We have negative v naught y squared over 2 of g, and g is negative when going up. So that cancels these two negatives. So that's why we have this, and that's going to be equal. So and that's going to be so our v naught y is 15. So 15 squared over 2 times 9.8, which is 19.6. But let's solve. So if we do 15 squared, so we'll do that, and then we'll divide by 19.6. We should get about 11.5-ish, 11.5 meters, yeah. So that is for this point, actually. So we're not taking into account this extra 25 meters of distance down here. We're just taking into account how high it goes in total. So now that we know it's about 11.5, we can put it into our time problem, which is 2 times d and dy, in our case 11.5, and that is over 9.8 because that's what gravity is. And so we can just solve now. So 2 times 11.5 and then divided by 9.8 and then square root that value, get about 1.5 seconds to max height. So 1.5. I'm gonna do 5.3 because that's our next digit. So we're gonna get about 1.53 seconds to reach max height. Now to find everything else, I take this max height and I add it with the cliff height. So you can see this kind of makes sense because if it's going up 11.5 meters, it's still got to go down 11.5 meters, and then you got to take account that we still have 25 meters still to go down, if that makes any sense. So I like to do this plus 25 or whatever the cliff value is. It doesn't really matter. And that'll be equal to 36.5 if I did my math right, which it is. So yeah, that is correct. So that would be in total for this entire thing. This this going all the way down is about 36.5 meters. And so now all we got to do here is just find the time for this value specifically. So this is kind of what I was looking at, and that's it. And then what we do, so we do the same thing. We do 2 times 36.5 over 9.8. So we do all that, and that's going to be equal, and that would be equal to our time value. So if we do 2 times 36.5 divided by 9.8 and then square root whatever that answer is, 0.489. Okay, we get about 2.7 seconds. So 2.73 seconds. So that's what we get. And now all we got to do is add these two values together, and then we can solve for d of x, because we're looking for the total time, and these are how you find the total time. There's probably an easier way. You could probably solve for this and then double the time, find the total, and then solve for the 25 meters and get the same thing. But you just gotta, all we gotta do is combine. So 2.73 plus 1.53 is equal to and that is equal to 4.26 seconds, or just about. So now we obviously know d of x is equal to our horizontal velocity, which we know is about 26. So 26, that would be times 4.26. And if we just do that, we multiply that by our 26, obviously. Multiply 4.26 by 26. We can get that it takes, so I'll just move this down here for ease of viewing. So we can get that it's about 110.76 meters, and that would be our answer. That's it. That's all you have to do. It looks very intimidating, but it's actually quite simple to solve for these cliff problems, especially considering the fact that all of these are is just a parabola that extends a little bit, and then we just gotta take into account that we have an extra dy value. That's exactly why this value is still considered dy. It's just because we're taking that into example. And yeah, so that's realistically it. That's it for this episode, and I hope you guys enjoyed it. or learn something from it, because this is actually quite a simple but very deceiving concept. It quite seems like a bad concept. It's kind of like very difficult seeming. And yeah, that's really gonna be it for this bit. And yeah, that's gonna be it. I will see you guys in the next tutoring video. Goodbye.